All right, mechanisms. This is the last topic for organic. You'll be happy to hear. Organic ends with a bang here. This is not going to be easy. This is definitely a second. Most of organic was a second-year course in college. All right, the stuff you're going to see there. Granted, you're going to go into a lot more detail, and you're going to have to do things that I didn't make you do, like, for example, memorize those reactions, as well as doing longer synthesis problems. However, for the most part, you saw a taste of pretty much everything you would see in the beginning of an organic class, all right? I just didn't do it in as much detail. This is like the second semester organic, this stuff, honestly, I consider it. It's really that hard. We're going to talk about mechanisms. Again, I won't go into anywhere near as much detail as you'll see in college, but it's going to be hard enough because today we're going to talk about not just what happens in a reaction, but how it happens. You know, you memorized before. No, you didn't memorize. You actually just had a sheet. You knew before what happened in a reaction, like Rx plus whatever yields whatever, and you looked at the general formula using R and knowing X means halogen, and you put them together. All right, well now I'm going to break down for you how that reaction occurs in a step-by-step manner. Because it doesn't happen all the time in one simple step. Sometimes it does. Actually, there are some mechanisms. There's one mechanism in particular I'm going to show you that's a one-step mechanism. But this first one I'm going to show you has, well, probably 6 steps you're going to have to know to recognize and identify. But there's other ones that could happen as well, as you'll see. So this is how a reaction occurs. Now, most of you are probably going to say to yourself, why do I care? Okay, that would be a good question at this point. Because even, for example, I know most of you aren't going to be chemists. And so this is probably the one topic that is even of less interest or less use to anyone out here. I try to make it as, most of the stuff by putting those videos and stuff like that in there, try to give you some relevance to real life. But this is impossible to do, all right, unless you're going to be a chemist. Understanding the mechanisms, why should I know? Bad enough I have to know what happens. Now I got to know how it happens in a detail. I mean, why? Well, there are actually 2 reasons if you're going to be a chemist, okay? There's actually 2 reasons. The first reason would be unrelated reactions, some that you would think are unrelated, actually proceed by a similar or the same mechanism. There's quite a few reactions actually on that sheet of 25 reactions that would have gone by the same mechanism. Now this makes life a lot easier for actually memorization, for actually understanding what's going on and then applying that knowledge so you don't have to actually memorize 40 reactions, each one as an individual entity. Instead, you know that there are all the SN1 reactions or all the SN2 or all the electrophilic addition reactions that proceed by that same mechanism. They may be adding water this time instead of HBr, instead of HCl, but they all do the same basic thing. All right? You may get an alcohol instead of a halide, but it's the same basic reaction. All right? Because look at I just put this up here, not that you ever have to know this, but take a look. Turn that light off so you can see the pretty weak slide here. Look at all the possible reactions. I mean, it's by no means all the possible reactions, but look at how complicated it can become. If you had to memorize every single one of these 40 or so or 50 reactions, you'd have a real hard time. But luckily, many of them go by a very similar mechanism, and a lot of them are just basically normal, kind of a common sense kind of things. What's going to happen if you put 2 things together? Notice how alkenes is right there in the center. Did you notice when we did our synthesis how many times you made an alkene? Remember, to get something else? Okay, that's very common. All right, and there's a lot of things that alkenes use for as an intermediate or to make something else. All right. But the point is, first reason I would want to know this, first reason I would want to know about mechanisms is to help me not have to see every one of these reactions as a separate entity, but rather classify them into different types and therefore make it easier to remember and easier to understand and easier to use. Can you turn that light back on? Now, the second reason I would want to do this, again, only if I'm a chemist. I'm not going to do this if you're not a pharmacist, research or a chemist trying to make a product, But if I know the mechanism, I can manipulate the mechanism to try to get more or better product, okay? I can adjust things. I can adjust what solvent to use because I know it's got to stabilize this intermediate. Or I can know what halogen I want to use as my leaving group because I want this guy to, you saw, for example, one of these I'm going to show you again, I think. I think it's under SN1 or SN2 mechanisms, where one guy will actually react faster than another one. And if I know the mechanism, I know why. And I can therefore change the circumstances of my reaction to make me have more product or faster product or cheaper or purer or whatever. So those are the two reasons I actually study mechanism. Now, again, neither of those really affect you. If you're just going to be taking chemistry as part of, one of your whatever science you're going to take, you're not really going to go into making things in chemistry, like in pharmacy, like in industrial chemistry or something like that. So I'm not saying you're going to see, you're going to have a whole lot of use for mechanisms in your everyday life, even as a science person or a biology person. But that's the reason you do it. Okay. Now, having said that, this is a tough topic. I'm going to go over 3 very representative mechanisms, ones that you would absolutely see in organic class. There's no doubt about it. Okay. And the first one is called free radical substitution. Now, free radical substitution, as the word implies, is a substitution reaction, which means I'm going to lose one thing and get something else in its place. All right, that's what substitution means. And free radical, I'll have to explain what that means. You've heard about free radicals. Most of you nowadays are in the news about, for example, you have antioxidants, vitamins and stuff that you take to try to gobble up these free radicals because they cause aging and they cause cancer and they cause all these other things. And that's true, but we're not talking about it in a biology perspective. We're talking about it in a chemistry perspective, what a free radical does. And basically, this reaction is a chain reaction. And you'll understand that as you see it happen, when you see the steps of it, how each time time a step happens, it generates a particle that keeps the reaction going in a chain reaction. You may remember last year we had one of the things we talked about in nuclear under chain reactions was a nuclear chain reaction. And the example there was a video clip I showed you. Maybe you remember it. Ping pong balls in a chamber, and there were basically 2 ping pong balls on each mousetrap, or actually I think it was a puff of air. But there was also one with mousetraps. Remember that one? There was 2 of them I showed you. You throw in 1 ping pong ball, it sets off a mousetrap, 2 ping pong balls go off, sets off the other mousetrap, keeps the whole thing going. It's a chain reaction.
That's like you ever seen the movie Mousetrap?
No.
Oh, so that happens.
Never saw the movie Mousetrap, but I believe you. But so that's what has to happen though. Every time you get one of these steps, it keeps the thing going because it gives you a product, it gives you something that's going to keep this reaction going. And the something that keeps it going, the ping pong ball that keeps it going, is called a free radical. That's the guy who's, as the word implies, very reactive. He's radical. All right. Now, here's the overall reaction for this guy. You've seen it before. If I take CH4 plus Cl2, I think you already have this on there, right? If you take methane plus chlorine, no one will be surprised. It's right there on your sheet from last chapter. You don't have to worry about it for now. It said an alkane plus a halogen. Alkane plus X, it probably said, or maybe RH plus X, however I wrote it, is going to give you CH3Cl plus HCl. Again, it would be X instead of Cl because I'm just using chlorine as my specific example. Okay? Now, that's the overall reaction. That's all you had to know for the last chapter. If I gave you that guy, many of you used him as part of your mechanisms. I'm sorry, as part of your syntheses. You do that as your first step, so you turned them into a halogen, and then you were able to turn that halogen into something else. Great. How does that reaction actually occur? Well, it takes a bunch of steps to actually get this thing to happen. All right. Now, before I start this mechanism, I want you to understand, mechanisms cannot be proven. I cannot see this happen. I cannot see a chlorine get broken apart. All right. I cannot see an H leave and a chlorine come in. I can't see these things actually happen. It happens too fast. And it's at the atomic level. And no matter how good of a camera I had, no matter how good of a microscope I have, I couldn't actually see it. So you might say, well, how do I know this is what happens? Well, most mechanisms are considered, you actually say the word postulate. They're postulated to be the mechanism that we think happens. And some reactions, believe it or not, actually have more than one that you don't even know. We don't even know for sure which one, if there's more than one possible mechanism this guy can undergo, because I can't see it. All right, and it can be, as long as they're consistent with the facts. And the facts are always through indirect observation. So let's take a look at what the indirect observation shows about a free radical mechanism, the mechanism for a free radical halogenation. We believe, because of studies and tests that we've done, that the first step of the free radical halogenation looks like this. It's called the chain initiating step. You can write that in there. Now, there's a couple of things I need to explain to you about this. First of all, do you remember what, in a reaction, what delta and lambda stand for?
Change in light.
Heat and light, exactly. Change, delta does mean change in a mathematical equation. But in a chemical reaction, we've seen it before underneath arrows, and it means heat. And the lambda means light. Actually, lambda usually means wavelength, but in the case of the generic means, it means light. And what we find is, through experiments, we believe this is the first step because chlorine is most susceptible to a particular wavelength of light. If we carry out this reaction at that wavelength, it happens fastest. Okay? So we know that it's very susceptible to that. We figure that's probably what's going to happen. There's other reasons too you'll see as we go along. Now again, this is going to be tough. You've got to follow me here. You've got to pay attention because this is, of all the topics we've done, there's no labs involved with this. Obviously I can't do a lab on mechanisms. I do have, however, a computer lab we're going to go back there and do. Probably could even start it today. I don't know how far we'll get. I might just be able to explain it to you. There's a new program, or not a new program, but an old program that you have, but you only haven't used this year. All right, but we believe this is the first step, and the first step is basically turning chlorine into two free radicals. Now, what does that exactly mean? Why is there a little dot? Do I have to draw that dot? What does that dot mean? Let me explain. Yeah, most of you didn't even see the dot. That's why I'm saying this, okay? Now, let me show you. What I'm saying happens here. Don't have to draw this. If you want to, actually, you can. There's like a big space up above. If you want to, you can actually draw this up above. What I really want you to leave room for, though, is to draw a beaker that's going to have stuff in it. Maybe make it a little bit more sense to you. But let me show you here. Oh, hold on. Here's chlorine. Chlorine, the molecule, looks like this. I think if I had you draw the electron dot notation, or what was called a Lewis structure for chlorine, you would have drawn that, right? Because you know chlorine by himself has how many electrons? 7. So by himself, he looks like this. You put the two of them together, that's what they would do. I think everybody would do that. Now, what I'm saying happens here is this. The heat and light split chlorine into something it does not want to be, which is 2 chlorine atoms, which we call free radicals. And of course, each one of them is going to have this unpaired electron. That's very unstable. You know that from quantum mechanics back when we did that in Chem 1. Everything wants to be filled or paired up at least, right? Remember? Everything wants to be filled or paired up. Octet rule, all that stuff. This guy was happy. He gets broken apart. And now he's got this unpaired electron. Notice I don't draw all the electrons around him, although I can. And sometimes if you look, matter of fact, on my last board I'm going to show you here on free radical halogenation, is going to show you how, I copied, if you copy or you look at other, internet or textbooks, they may draw all the electrons, and it might look like this. Okay, it might look like that. That's fine, all right. But most people just tend to leave them out just because it makes it easier to draw. And certainly I will, because it makes it easier for me to draw on my tests and on my worksheets. I don't have to draw all the dots around. Now, as you probably figured out, that guy is your free radical. He's crazy. He really wants another electron from somebody. He will take it from anybody. If he bangs into anything, he's going to rip an electron away from him. Okay? Now, here comes the question. The reason I want you to draw a little beaker up above in that space. Okay? What could he bang into? Well, let's take a look at, here's my beaker. And I'm going to draw this. No, I'm not. I'm going to draw this so I can come back to it. All right? So I want you all to draw this. Here's your beaker. Great beaker. All right. There's your markings on it. There you go. Great beaker. Now, you have to make it pretty big because you're going to be writing some stuff in here. All right. What's in that beaker in the beginning? Take a look. In the beginning, if we take a look, that's my reaction. I throw in methane and chlorine into that beaker. Okay, granted, they're both gases, so it can't be just a beaker. It's got to be a chamber, but whatever. All right? I throw methane and chlorine into that beaker. That's all that's there. Okay? So let's go back now. Here's my beaker. what do I have in here? I've got methane, and I'll make him blue. No, yeah, I'll make him black. Here's I have methane molecules around, and you can draw a few of them. And I've got, God bless you.
Thank you.
I've got chlorine. Let's make chlorine blue because I can still see blue. I got chlorine molecules, even though I probably should use green, but you can't see it very well. So in that beaker are gazillions of methanes and gazillions of chlorines and nothing else until it starts, correct? Then, all of a sudden, I turn on the lights, I turn up the heat, and I split, I cleave one of those chlorines. And I make a chlorine-free radical. We'll make him red. There he is. He's like a little Pac-Man. He is going to gobble up an electron like Pac-Man. Remember old Pac-Mans? Yeah. Gobble up those little dots. He wants to gobble up an electron from anybody. So, the first chlorine-free radical is made. By the way, all this is going to happen to these gazillions of atoms in a split second, in less than a split second. But I'm slowing things down for you. I make that first chlorine-free radical. What could he bang into? Two things, right? What are the two things he could bang into? He could bang into a methane, or he could bang into another chlorine. Let's do the other chlorine first. Don't write this down, because it's not going to be one I'm going to actually write in the sheet, and you'll see why in a second. If my chlorine-free radical, and I'll draw all the electrons around him this time, all right? So I see one, there's my chlorine-free radical. Bangs into a chlorine molecule. What's going to happen? Well, he'll rip one of these guys away, right? But what does that do? If he rips him away to make this into a chlorine molecule, what did he actually end up doing anyway? Making another free radical. So what's the point of writing that one, right? There's not really any point of writing that guy because you make exactly the same two things. All right, good. But if he bangs into the methane, yeah.
Is that equally likely to occur, or is it?
Well, yeah, exactly. In the beginning, you have to keep this in mind too. Good question. In the beginning, you have an equal chance. If you assume you have equal amounts of these, an equal chance of him banging into this guy or banging into that guy, right? Could happen, and probably does. But you never know if this guy happened because you just regenerate the same thing anyway. The other 50% of the time, he's going to hit these guys, right? Let's see what happens there. That's more important. That is what's called a chain propagating step. If he bangs into a methane, he will rip an H away from him. That's the easiest thing for him to rip away. Take an electron with him. Take one of the hydrogen electrons with him. And make, by the way, HCl. What is HCl? HCl is one of my products. Take a look. HCl right there. He's one of the products, isn't he? So I just made a product. But I also made something else. What else did I make? Well, think about it. Again, I'll draw this one out. You don't have to, but I'll draw it out for you. Here's methane drawn out as an electron dot notation. Okay? There he is. When that chlorine-free radical takes him away, what is he taking? He's taking that electron with him, isn't he? What does that leave behind? Now, another free radical. I leave behind what's called a methyl free radical. And by the way, this is different than just methyl, all right? See, this is a methyl free radical. Methane, for example, it's a methyl free radical, okay? So he is just out there. He's not attached to something. Like, we always call this a methyl group, all right? And that is a CH3. That's a methyl group that's attached to something else, okay? This is just floating out there in the middle of my beaker. Well, that's, again, same exact reactivity of the chlorine-free radical you have. He is like Pac-Man. He wants to gobble anything he bangs into. He's going to rip an electron away from. Let's go back to my beaker. What could that methyl-free radical bang into? Now I've got a methyl-free radical. I'll keep him as red too. We'll call him CH3 dot. All right. What could he bang into? Again, in the beginning. Yes, you formed a little bit of HCl now, but in the beginning, what's the most likely chance of him banging into? You can bang into two things, CH4 or Cl2. If he bangs into a CH4, is there any point in writing that out? No. But if he bangs into a Cl2, What's going to happen? Well, as you'd expect, that.
Well, couldn't he bang into HCl?
Absolutely, I just said that. You formed a little bit of HCl. I did say that.
Right,
But how most chances are he's going to bang into these other guys. Right. And by the way, if he did bang into the HCl, what would he just do? He'd just rip off an H again, right, and start it all over again. Exactly. All right. So now let me put this in perspective. Now that I've explained all this to you, and hopefully you understand it. All right, because we're not quite done yet, but we have gotten through the chain reaction part. The reason these are chain propagating steps is that they do two things. They form a product. By the way, there's your other product, CH3Cl. Remember, if I go back to the overall reaction, that's the second product, the first product. That's the second product. But they do something else. They also form a free radical that goes and continues the process on in a chain reaction until what's going to happen? It's going to go and keep doing this in that beaker until all those things are used up. All right? And I'm going to do that until they're all used up. And eventually, will you still have some Pac-Man molecules going around? No, because as I use these guys up and start making more and more product, there's less and less of the methane for it to bang into and less of the chlorine for it to bang into, right? What could it bang into that would stop this process? What could, as more and more of these free radicals are formed and less of the reactants are around to bang into, what could they bang into that would end the chain? Exactly. They could end the chain by banging into another free radical. So a chlorine free radical, it doesn't, in the beginning, what's the odds of that happening? It's very slim. But as time goes on and you make more and more free radicals and you have less and less reactants, because there's no point in him banging into a product. If he bangs into a product, he's either going to reform the same product, but it's at a lower energy anyway. So there's no real point in that. All right. If he does this, it's not going to change a whole lot. So in other words, if one of these free radicals bangs into a product, he's going to replace the chlorine on it. Big deal. That's the same exact thing. You know. So eventually they will bang into each other. So of course you'll get a little bit more chlorine back, and he could be broken again and start the whole process over. These two guys can get together, right? That's possible, right? The two free radicals for that guy. That's the second chain terminating step. Why do we call these guys chain terminating steps? Because they take free radicals and you end up with no free radicals. Now, I told you all of this is done through indirect observation. How could they know this is exactly what happens? Well, again, we can't know it. We postulate a mechanism. Mechanisms are not known with certainty, period, anyway. But secondly, we have other reasons besides the fact of the wavelength of light breaking up chlorine. And here's the other one. This is a great one. I love this one. What else could happen? What other two free radicals could bang into each other? Two CH3s, right? Now I want you to go back to this reaction again. If I told you this plus this yields ethane, what would you have said? Doesn't make sense, but it does. That's the crazy part about this. You know what one of the side products of this reaction is? It doesn't happen to a lot. Get a very small amount of it, but one of the side products when you add methane to chlorine is you'll get a little ethane. And that's another evidence that this must be what happened. You see what I'm saying? They didn't see the methyl free radical form. They can't see the electron, the unpaired electron. It's not possible. It's too small, it's moving too fast, and it's happening too quickly. But you can see that there was ethane made. And that shouldn't have been there. There's no reason for that to have been there. Yet there it is. How? Well, by postulating that we had free radical methyls formed somewhere along the line in this process. Now, how might I ask? Now, we're done. That is it. And you have the definition already at the bottom of your thing for free radicals, right? Which basically looks like it's a very reactive atom with an unpaired electron. All right. Now, let me tell you, as far as you're concerned, that was the best I can explain it. But as far as you're concerned, what do you want to know for the test, for the worksheets? How can I ask questions on this? Am I going to ask you to redo this whole thing? Well, first of all, let me say, these are the kind of questions I could ask you. I could say, hey, circle all of the free radicals in the chain initiating or chain propagating steps. In which case, you would have the circle. You know, all the free radicals in these steps would be here, 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 and here,
You
right?
have the dots by them?
I will. So it's really easy to
Well,
tell.
that's what I'm thinking.
Yeah, exactly. All right, so that's easy. I could ask you, without labeling them, which of them are? Which of these steps are chain propagating? Which of them are chain terminating? Which of them are chain initiating? And that's easy too, isn't it?
Yeah.
Chain initiating are going to start with no free radical and end with a free radical. Chain propagating, have them on both sides. And then chain terminating, get rid of the free radicals, right? I could ask you to box all of the guys who make all the products. How are they made? Here's a product. Here's a product. Here's a product down there. Huh? You missed that one, right? I could say, what's an unexpected side product to this process? And you would say it's that guy, right? You wouldn't expect him, but that's what happens, right? Those are the kind of questions I would ask on a reaction like this. Okay, so you know.
What you would consider a product is something on the right that doesn't have an unpaired electron?
Well, I would consider a product. Hold on. Remember, the overall reaction is right there. Those are the products, right? So basically, those are whatever reactions, whatever steps form those products. All right. This is not. This is a side product. That's not something I would expect to happen from CH4 plus Cl2. But yeah, I understand what you're saying. The technical definition of a product is anything on the right-hand side. All right. But I'm not talking about the free radicals that are also regenerated. All right. I'm talking about the actual product of the overall reaction. Okay. All right. And here, I'm going to stop this here.